All right. Good afternoon. Well, I know I'm speaking to great people, so I trust you can identify with the thought for this week. All right. I had planned to send you a message, but if you could just access for me the lecture notes, should be available in Schoology, and pull up the information on distance relays. Let's make sure it is published. And so on the lecture notes, you'll find distance protection and pilot schemes. All right. Okay. So with that, you would have all the figures that we'll be looking at today. So you won't have to be drawing these, but I'll be saying some additional stuff that is not contained in the notes. So you just make your jottings accordingly. All right. So, yeah. So we're going to be looking at distance protection and distance protection schemes. Now, in looking at relays, we had spoken about the distance relay. We had spoken about the settings. One of the things we did not delve into were the characteristics, the various characteristics for your distance relays. So we had only mentioned the mode characteristic, and we don't, well, not in detail, but I did give you a picture of a general directional impedance relay with circular characteristics, and then we spoke about the mode characteristics in terms of having systems that based on the load type would cause operation, then we use the mode. There are other characteristics. That's what I really want to mention. The fact that there are other characteristics, you have quadrilateral, etc., etc. Now, we're not going to delve into that. If you decide to come back and do some advanced work in protection, then sure, we'll delve into that bit of study. But for now, I just want to alert you to the fact that there are different characteristics which will be used based on the system that we are seeking to protect. Now, there are the distance protection as we know it, as we have presented it thus far, looks at zone settings. So we have zone 1, zone 2, zone 3 settings. And of course, for your zone 1, which we have indicated goes up to 80% of the line from the relaying point. In terms of its operating time, that is instantaneous. For your zone 2, you would have up to 200 milliseconds. And then it also increases thereafter to 300-400 for your zone 3. Now, in terms of the settings, we also spoke about the fact that for zone 1, as I mentioned just now, you have 80%, zone 2, 120, and then zone 3, 100 plus 120 of the adjacent, etc., etc., etc. So you have all of that data. The question is, how do we ensure that should we have a fault on the line, that both ends of the line can be cleared in the fastest possible time? And before we answer that question, we just want to, well, what I was just saying, here it is. Yeah? how do we ensure that we have clearance in the fastest possible time? And the real challenge occurs at the what we refer to as the end zone of the line, because and part of the let me step back here. Part of the reason we have our zone 1 setting at less than 100% is that we're dealing with a transmission line. You have environmental factors that are going to be at play. Your relay, yes, it's in an area with which is temperature controlled, etc., etc. But things do happen, and so you do not want to have a situation where the protection is operating for lines outside of the protected zone. So to be on the safe side, we're at 80%. I also mentioned to you that our own utility here in Jamaica uses 90%. All right, but the standard is 80. So there is always that 20%, or in the case of JPS, there is always that 10% of the line that would not be under the zone 1. And if a fault occurs in that latter portion, what we call the end zone, if we have a fault occurring in the end zone, the challenge is that at one end of the transmission line, that fault will be seen as a zone 1 fault because it would have been within 20% of the length of the line. Agreed? But from the other end of the line, it will be seen as a zone 2 fault. So the question is, and in your, let me see if I can go back now, because we try to tie up everything in these 2 modules that I have done with you. If you go back to you remember that load flow lab that you did in power systems, where you disconnected the line from one end, but you still saw that power was being consumed by the line. You remember that exercise? Okay. All right. Now that exercise, very important lab, because what it is saying to you is that when you switch out a line, you have to switch it out from both ends. You can't disconnect one end and say, yes, the line has been switched out. It has to be removed from both ends. So if you have a fault on the line, you need to open the breakers at both substations at which the line is terminated. All right? Now, herein lies the challenge before us. If it is that the fault remains on the system for zone 2 time, it may cause the system to become unstable. Yep. I don't have all the details as yet, but recently there was a power outage, all island blackout in Trinidad. Yep. And it just cascaded. So that is something they're simply not accustomed to. I mean, Trinidad operates in such a way that the generators there, they don't even buy the fuel. The fuel is provided by TNTech to the generator. So there is really no expectation to have loss of generation. However, because of a fault, as I said, I don't have all the details, but because of a fault in the system, which escalated, they end up having a total island-wide blackout. All right? So we want to ensure that that instability that can come from you having one end of the line remaining connected to the system with the fault. Yeah? Remember now, you don't know what type of fault it is. All right? But there's a fault on the line, phase fault, which means that there would be contribution into the fault from either end, because again, we are running an interconnected system. But if you are in the end zone, it means that you would have clearance in zone one time at one end of the line, but then you will continue to have feed from the other end into the fault point. So as part of our main objective in terms of protection system for the line, we want to ensure that both ends can be removed from service. So you want to have the breaker opening in as short a time as possible. If it is, or if it was that we could do so, without delay, if we can do so instantaneously, that would be ideal. But as we go through this afternoon into this evening, what you're going to see is that although instantaneous is ideal, we try our best to ensure that the clearance or the opening of the breaker needs to happen. So there are mechanisms actually built in to ensure that it is not instantaneous. I hope that makes a little sense. All right? Okay, so the first one is that we don't want one end to maintain the zone 2 timing, yes, while the other end is instantaneous, because it's going to result in instability. The other point we're making here is that if you have high-speed auto reclosing, where in terms of the operation of an auto recloser, it's a breaker, but in terms of its operation, what you have is that if there's a fault, yes, you want, and it's usually, this is usually done in remote locations or very important circuits also. If you have a situation where a breaker operates, or you have a fault on the system, and let us say the fault occurred as a result of, let me try and find something that will be temporary. Let's say you had high winds in an area, and because of the high winds, you then had a tree, swaying, and branch touches your transmission line. Immediately you have a single line to ground fault or a double line to ground fault. Yes? But because it is windy, the fault doesn't remain. So it triggers, operates, opens your breaker, but the auto recloser will seek to reconnect the system without human intervention. All right? So that's how the auto recloser operates. So it seeks to reconnect the system without human intervention. What we are saying here is that if you have that in place and you remove one end, that's your hand, Mr. Duncan, and you remove one end before you open the other end, then the time in terms of the auto reclosing, the time for the breaker to open and the necessary gases being extinguished, and you have deionization of our gases, yes? Then when the auto recloser seeks to bring back the line into service, because one end is not cleared, it will basically be bringing it back onto a fault. You with me? So the fault itself may have been removed. However, because the both ends did not open simultaneously, you will have one which still has, and I'm stretching it here, but you may still have that arc on one end, while one end is clear. But then when you re-energize, it reconnects the system onto fault, all right, or onto a fault. Yes, Mr. Duncan.
Yes, sir. I think a good example of this would be when sometime when the power is going, sir, you'll see it go off and then it comes on back short after and then it repeats for a couple of seconds and then it eventually goes off completely.
Yeah. Even though sometimes that is as a result of transients. But you are onto, yeah, what you are saying is true. So what the auto recloser does, and this now is by policy. So what I'm saying now is by policy from the particular utility that you are going to work with. By policy, the utility will determine how many times the auto recloser cycles. So in some utility, it allows one attempt. In some utilities, it will allow 2 attempts. Yes? So what you have is that the fault occurs, breakers open, auto recloser seeks to re-energize. If it re-energizes and the fault remains, it will open again. But because of the setup that we have, if we did not deal with it, because what we're going to be talking about this afternoon is how we address these problems, right? That's what the schemes are all about. So if it then re-engages a second time and still sees the fault occurring, then it opens and it locks out. So at that stage, human intervention will be necessary. So the utility would now have to dispatch its crew to the various locations to reset the breakers. All right. So to avoid these scenarios that I have mentioned, the instability, and if you are using reclosers on the system, auto reclosers, then you don't want the system to lock out. We have to look at all these protection schemes. So I'm going to come back to this because this is your standard distance protection, and we'll just come back and talk about what this is showing. But just go back to the end zone discussion that I had just now. What we are saying, here's my line. Yep. This is bus bar A, this is bus bar B. And for zone 1 protection, we have it up to 80%. So up to 80%, that is zone 1. Okay? And then with my adjacent line, I have for my zone 2, I'm going over by this would now be over 120%. All right. And what we're going to be showing you, it has zone 3 having 10 to 20% behind. So you'll have the other line here, and then your zone 3. I'm just going to put it at the bottom here. Let's try to find a different ink. Hopefully you'll see the green. So zone 3 would continue. All right. As I said, there's a reverse portion of zone 3. All right. And this would be the 100 plus 120%. That's your zone 3. Okay. So the end zone that we are talking about, your end zone would be here. So if we have a fault in here, if the fault occurs in the latter 20% of the line, that is where we have a problem. Everybody with me? If the fault is here, The fault is in the, remember the red one is the original line. If the fault is in the middle of the line, at end A, the relay at end A, which is substation A. Yeah, I'm at that stage where I need cut liver oil. Anyway, at substation A, it will have it as a zone 1 fault. Good? And we know that zone 1 is instantaneous. So substation A would be instantaneous. Okay? Substation B would also be instantaneous. That is for fault F1. For fault F2, which is up here, yeah, what we are saying is that substation B would be instantaneous. However, substation A would see it as zone 2. You with me? So this would have the 200 to 300 millisecond time delay because it is seeing it as in the zone 2 setting. But the fault is on the line AB. Yeah, the fault is on the line AB, and ideally, because it is on AB, we want to remove breakers at both ends as fast as possible. So everything that we'll discuss this afternoon, yeah, we'll be looking at how to increase or reduce the time taken or increase the speed, yes, of operation in this instance at substation A. All right. So there are a couple of things. There are a couple of things I want to highlight before we go any further. Have you accessed the document on Schoology?
Yes, sir.
All right. All right. So I'm going to go back to the figure we just looked at. So here is the fault. All right. It's in the end zone. And just to help us appreciate the logic circuit and of course the solid state, I don't need to go through that today. You're all experts where that is concerned. But just to help you appreciate some of this, couple of things we want to note. We have our zone 3 up top. It's off the page a bit. We have our zone 2. We have our zone 1. And note that those are zone 3G, zone 3, 2G, and zone 1G. All right, so at the top there, we have, and so these settings up here, that is with respect to substation G. At the bottom, it is with respect to substation H. Because remember, one of the things we mentioned when we spoke about the distance relay is that it is directional. All right, so it's looking in a direction. So G is looking towards H. So it will only see faults ahead of it, towards H. And H is looking towards G. So it can only see faults in front of it. Of course, you know, in terms of let me not confuse it with that. All right, so those are the settings. The next thing I want to highlight, if you go now to the contact diagram, and just to distinguish the contacts that we have there. So zone 1, the Z1, Z2, Z3. All right? These are all instantaneous contacts. So I know I've been telling you about zone 1 being instantaneous. That is true. However, in your contact logic, Z1, 2, and 3 are all instantaneous contacts. All right? What do you call it that? All right, no. So Z1, 2, 3 are instantaneous contacts. Now, for Z2 and Z3, whilst they are instantaneous contacts, what they do is to connect the Z2 timer and the Z3 timer to the power supply. So the instantaneous, so the Z2T that you have over here, those are timers. What do you think? So this would give you your 200 milliseconds. This would give you your 300 or 400 milliseconds down here, all right? Okay, so with those timers, once the time that is set have elapsed, you would then have your Z2T and your Z3T contacts in operation. All right, so I pause there. Have I lost you?
We're following, sir.
All right, I'm going to pull I'm
Yes, sir,
pulling
we're
everybody.
following.
Following. You see, I know you're my super group, you know, but I have to be careful. All right. So your Z2T and we denote that. If you look at the bottom here, you see a little arrow. Yeah. So the little arrow is telling you that the contact will close after a time. So we close that after the timer here. And that's what these are showing. So these, you will get your 1, yes, after the Z2T. So you'll get an output. So it is 0 prior to the Z2 time, and you'll get the 1 after. So of course, with your OR gate, you'll get a trip signal for 1 of 3 signals coming. 1, whether you get a zone 1. So if it is a zone 1, it's instantaneous with our OR gate, yes? If you get a timed zone 2, you'll get trip. Or if you get a timed zone 3, you'll get trip. So based on all of this, what we're saying is that if I had a fault at this point, right? So let's call that point 1. Let's put another one here. Let's call that 2. And let's put 1 down here. All right. And I'm going to be looking at end G. So at end G, for fault number 1 at end G, I would get an instantaneous. And so I will get a trip. Good. If the fault is at point 2, if the protection between H and J does not operate, then I would get operation at NG only after Z2 time has passed. And that is how the backup comes in. Because it is expected that the instantaneous operation on HJ would have operated. And then finally, if the fault is all the way down at 3, then it means that the backup that should have been provided by HJ would also have failed in addition to the primary of J, and we assume that that is K down the road. All right? And so in those circumstances, it will operate after zone 3 time. All right? Okay. So, remember, with all of that said, we are now going to be looking at ways in which we can speed up the operation from H. Yeah. So if we just look back with this fault, note it is in the end zone. It is zone 1 for H, but it is zone 2 for G. And that is the problem we are trying to solve. We're going to try and solve in the next hour or so. All right? I will look at all these systems. So you have some notes there, but as I go along, we will say things that you will want to make your own jottings. So the first scheme we're going to be looking at is the zone 1 extension scheme. Now, your zone 1 extension scheme, it is used where you're having challenges in terms of communication. Because to achieve the goal that I have just set, which is how do I ensure that both ends operate quickly? To achieve that, we require communication between the two ends. Right? So there has to be signaling, there has to be communication between the ends. Whether it is that when the fault occurs at G or at H, as a zone 1, it tells zone 2 that I have operated. So there is communication. However, where you have circumstances that you cannot rely on the communication channel. So for whatever reason, you have some issues. Let us say, and I suppose this is quite applicable to Jamaica, no? and I am saying it and my heart hurts because it is a truth that should not be. But anyway, as it is, our utility currently uses fiber. All right, so all the substations are connected using fiber. And the fiber is not necessarily owned by JPSCo. Right? The fiber network, surprise, surprise, is owned by Flow. Right? And it is I say surprise, surprise, because the competitor has taken Flow's own infrastructure and has used it better than them, right? But anyway, we leave that one for now. But the entire fiber network is owned by Flow. Good? Is Flow or Lime them name? Whatever, that one there. All right? Now, the utility uses that facility. So it has that fiber connection. And when you have a fault, the communication between the substation is done by fiber. Now, the reality is we have some strange people among us who, for whatever reason, decide that they're going to stop 5G coming. So they go and they chop the fiber cable them. And the bottom line is you lose communication between your substations. What do? Because you can't leave the system just open like that. And zone 1, the zone 1 extension scheme considers that possibility. So the extension scheme is not, and I repeat, it is not, considered to be a standard system, but it is used when you have challenges in terms of your communication channel. So, man, if you know, next time you pass a substation, I don't think they have removed them. You will see microwave antennas on top of the relay house. So that's what they used to use in the past. But of course, microwave is somewhat unreliable because it has to operate by line of sight. And to achieve line of sight is Jamaica you're dealing with. Jamaica is a fishbone. You have the range of mountains running right down the center of the island. So, you know, you will have challenges going across island. But yeah, when we get there, we'll talk about that. So when you have these challenges, this is where the Zone 1 extension scheme becomes helpful. So the settings for your Zone 1 extension, yes, you have both a 80 and a 120%, 120% of the protected line. All right? And the scheme is used with an auto reclose relay. So those are the two things that are considered for your Zone 1 extension. In terms of when it operates, what happens is that the relay will operate in Zone 1 time for faults that occur in Zone 2. So if you go back to what we were trying to solve with this end zone fault, if we had the Zone 1 extension, then G would operate in Zone 1 time, although the fault is in Zone 2. And that's where the extension comes in. All right, that's why we call it Zone 1 extension. So both ends would then operate in Zone 1 time. Now, it also initiates auto reclosure. However, once it operates, there's a contact from the autoclose relay which resets the Zone 1 back to 80%. Which is why I emphasized earlier that you are using this scheme not as a standard protection scheme, but based on the circumstances in which you find yourself not having the communication channel up and running. All right. So in terms of the contact diagram, if you note from end, it should be clear on your on the figures that you have there. All right. So up top you have here the Zone 1 G, and then you have the Zone 1 extension G. You see the dotted lines from here to here. All right. So the extension goes from the 80% up to the 120%. Or you can see it better at the bottom from end H, looking from end H. Yep. You would have, this would be at 80%. And then it goes all the way up there to 120%. So this is the extension in terms of your Zone 1. All right. So what we are now seeing is that wherever the fault is on the line, yep, you will get a Zone 1 operation. Because whether it is zone 1 or zone 1 extension, you'll have instantaneous operation. All right? So these contacts would give you instantaneous operation. Yes? And then when you come down here, if there is no signal from the artery close, so if you have no signal from the artery close, then when you get the zone 1 and there is no signal, then you would have gotten a 1 here because you have a NOT gate here. Do I need to say that again? All right, so let's look down here. All right. You'll get a 1 from the AND gate if you have 1 and 1. Yes? Remember we said that when you have the zone 1 operation, zone 1 extension, it operates the artery close. And a contact from the artery close relay will reset the system to its original 80%, 120%, zone 1, 2, 3. Yes? At the top, if you have a fault in the end zone, it would now be part of the zone 1 extension. So if I have a fault here, yes, it is within the zone 1 extension from H. Good? So I would have gotten a 1 here. But that would have occurred because I would have gotten nothing from the artery close. So I would have had a 0 at this point, but this is a NOT gate into the AND. So with the 0, I would get a 1. So you have 1 and 1. So that would cause the instantaneous trip from H. And I would also have had an instantaneous trip from G. One of the challenges when I teach this is to help students to understand that this figure that we are showing here represents what is happening at only one end of the line. So this is replicated at the other end. Are you with me? So if after operation, so work with me now, after the operation, you would have gotten that signal from the artery close. So you'd have had a 1. So you'd now have 0, which renders the zone 1 extension of no effect. So it allows you to have only one operation. That's the point we're trying to make, which is why it isn't something that you would install as a protection system. You are only using it because you have lost your communication network. So this is the zone 1 extension, for use of a better word, is really a stopgap. I don't like the looks on your faces, so ask the question. Well, Mr. Buchanan hide his face, so I can't see it clearly. But Ms. Gray looked rather perplexed just now.
Sorry, it's not really complex. It's just, all right. So, all right, I'm not saying we can explain it to you.
Yeah,
so see if I'm right. All right, so the fault occurs in the end zone. So we're looking at H, right? So say it occurs at 100% looking from H.
No, 100% is a bus fault. Let us stick to a line fault.
Right,
so
90% from H.
So it is, yeah, okay. So it is right here. Okay,
so
good.
In that case, this down where you circle, the zone 1 extension will get a positive 1.
Yes.
And at the same time, well, that would have tripped the relay, I tripped the circuit breaker, and the auto reclose would have also sent a signal back to this input to the AND gate again to reset it. So you'll get a 0 there, since there's a NOT gate.
Go
And
ahead.
that would produce a 0.
So this is when it is forcing the system to revert to the regular operation.
Okay.
So what is down here? What is shown? All right, so I have my fault here. What is shown here for operation is prior to a fault. So before you have a fault, this is what is shown. So you'd have 0. You wouldn't have anything from the auto reclose. All right? So you have 0. So it means that at this point, there's a 1 sitting right there into the AND gate. We good?
Yes, sir.
We now have the fault. You're now going to get a 1 here, and that 1 will give you a 1 on the AND gate. This is from end H, which means therefore that you would have a trip because you would have a 1 into the OR gate. But once it has operated, the auto reclose now sends a 1. So you'll get a 0 here. Yeah? With the 0 at that point, if you get another end zone fault subsequent to that, yes, the zone 1 extension would not work.
Right, so it classifies as zone 2 in that case.
It now goes back to a zone 2 and you get the normal operation as before.
Okay, then I understand.
Ms. Gray look better now. Thank you, Mr. Duncan. Okay. All right, so that's your zone 1, your zone extension. The next one we want to look at, and always keep in the back of your heads what our objective is. Our objective is to speed up operation at either end. All right? So the next one I want to look at is your transfer trip scheme. And your transfer trip scheme, it's quite simple, yes? It clears up faults in the end zone, in zone 1 time, right? What happens is that whenever a zone 1 fault occurs, it also sends a signal from the zone 1 contact to the remote end. Right? So your direct transfer trip scheme, which sometimes we refer to it as an underreaching scheme, but direct transfer. Once you have a zone 1 operation, it's going to send a signal to the remote end saying, I have tripped. But there's a problem with that. And the problem is this thing called noise. Noise, of course, is not what is being played outside, but noise is an unwanted signal. So if you have noise on the system, it can cause the remote end to trip. Because the remote end, via the communication medium, can pick up that noise and mistaken it for a trip signal. Right? So if I have the fault in the end zone at G, right? I don't know if I have a blank here. Oh, why is it chopping off my diagrams? Anyway. Well, you should have the figure there, all right? Sorry. Okay. So if I have a fault at the end zone at G, G would have seen it as a zone 1 fault, but H would have seen it as zone 2. I think we have said that enough, so, I don't need to keep repeating it. But anyway, so what we now do at G is that G would send a signal from its zone 1 to H. And once it is received at H, it will trip. So you see, this is G to H, yes? And at H, it receives. So this is at H. This is what is going from G to H. So the fault is a zone 1 at G, but it then sends the signal to H to say, I have a zone 1, and by virtue of that, H will trip. Because there's no timer here. So you get a 1, and so you get a 1. At G, it would have had its 1 and the 1 there. So this would be H1, and this would be G1. Again, I repeat, always remember that this is repeated at either end of the line. So H would also have a receive signal port. So or G would also have a receive signal. So if the fault was in the end zone at H, it would be a zone 1 at H, but it would send a signal to zone 2 to NG. As I just mentioned, the biggest problem with this system is incorrect operation. All right? Due to noise. And this is going to be dependent, as I said, on the medium that is used for communication. Because some media are less susceptible to noise. All right? So you can receive a signal thinking that it is a trip signal and trip when nothing was sent. But we can modify this system. Right? We can modify this system to ensure that there is some, should I say, more, word it eludes me. But anyway, we can modify this system by including what we refer to as a supervisory function. And this is known now as the permissive underreach trip scheme. So what we know? What do we know? All right, while you're right. But you have this in your notes already, but just give me a minute, I'll be back. All right, so your permissive underreach, right? The key here is that we use the zone 2 to supervise the signal that is sent, all right? What does that mean? With your permissive underreach, because the fault is in the end zone at one end, it would also see a zone 2 fault. But remember, before we started looking at the schemes, I identified the different contacts. We had an instantaneous zone 1, 2, and 3. And then we had timed zone 2 and 3. So it is the instantaneous zone 2 that provides the supervision. All right? Because immediately as a fault occurs, the zone 2 instantaneous would have operated. Yes? So what we do at the remote end is that we must see both the zone 2 instantaneous and receive the signal. And of course, I stress the and because it means that we will have an AND gate in operation. All right? So let's look at the permissive underread. All right? So down here, this is the instantaneous zone 2. Yes? And this is the receive signal. Now, the receive signal, there's a little addition to this. For the receive signal, we have a slight delay on the system. All right? So we hold the signal on the system, and I will explain why. But more importantly, permissive underreach, we still have the signal sent via zone 1, but it is supervised with the instantaneous zone 2. So the AND function occurs. Any questions? I know that we have gone through the tough one. Things are getting a little simpler. Huh?
Understand, sir.
A note here. This one says we release after a time t. So it is held there for a time t. And that's where the timer contact would come in. All right. Now, just to explain why it is that we would hold the signal for a time t. Yes? And I'm doing that showing this this double line, single fed double line system. What happens here? So the fault is on line GH. And what we are showing is that the fault current or the fault occurs close to end G. Right? And remember, the objective of me going through this is to highlight why it is that we delay the signal. We delay the receive signal. So we hold it for a little while. Right? With the fault closer to G, this would obviously be a zone 1 fault from G. However, at the time of this fault, because you have current contribution into the fault, you'd have current from G into the fault, but you'd also have current into the fault. Yeah? What you want to have happen is that both breakers, excuse me, don't worry, it doesn't spread across the computer. So you want both breakers F at G and H to operate, okay? But because it is closer to NG, this one would have operated in zone 1. At end H, however, it would say a zone 2 fault. Fair enough? Now, if you were to open this breaker in zone 1, the signal from G, that zone 1 signal, the zone 1 signal that is sent to H, technically would have been lost. Because you open the breaker. The breaker is open. You see? So you'd have lost it. However, if you delay the signal at H, if you hold it at H for a time T, when the zone 2, know that the contribution from H would increase because you have cut off the contribution from G into the fault. You would now have an increase from H. Can we see that? You have the fault at this point. You have current contribution from that end, from that end. The current contribution from here is small relative to over here. Because this breaker is open, the big current disappears. But it's the same generator. So you now have the fault current going all the way around. You with me? So now that H will see the current as a fault current after the breaker G has operated. It would have had to retain the sent signal in order to quickly operate. But if you had removed the signal immediately, then what would have occurred is that H would sit there and operate in zone 2 time. And so the fault would have remained on the system longer than necessary. Now, I know when we think about it, and we're talking about 200 milliseconds, and we are saying, boy, that long, But in the scheme of things, it is. In power systems, it is. All right, because we're dealing with very high currents. All right. You only want to get an appreciation. Just look at what happens when you arc a 9-volt battery. And then you scale that up and you understand the sort of damage that can occur in your power system. So this is the reason, or this helps to highlight the reason why we hold the signal, the sent signal, at the remote end. All right? Okay, so we have looked at the extension scheme, we have looked at the trip scheme, direct transfer, and we have looked at the permissive underreach. The next one we want to look at is the permissive overreach. And the only difference here, students, the only main difference with the permissive overreach is where the signal is sent from. So that's the primary difference. You have the notes there, but the main difference, oh, I had all of this written. Okay, you can write this. My bad. All right. All right, so we talk about the acceleration scheme. It's quite similar to the permissive underreach as we are stating here. But for these schemes, the difference is that it utilizes a special type of relay, all right? Where you have the zone 1 and 2 are switched on the relay. So the zone 1 and 2 settings are on the same, how should I put it now? Well, well, it's stated simply there, so I don't really need to add it. On the same measuring unit. So it is what we refer to as a range change relay. Yeah? So in terms of its operation, similar to the permissive underreach, but it utilizes a special type of relay. I suppose the utility, again, from a policy position, will determine when they utilize this. The drawback, however, is that because it is using the range change and it is switching between zone 1 and 2 on the same measuring unit, it means that with the acceleration scheme, they are going to be slightly slower. I mean, you might have better checks, but it will be slightly slower than your permissive underreach. Okay. So I'll just highlight that here. So here you have the zone 1 and 2 using the same measuring unit. That's the key difference. All right, so I want to run now to the permissive overreach transfer trip scheme. So for the underreach, we were sending using zone 1, and we were monitoring using instantaneous zone 2. All right, I'm running ahead of myself, but for your benefit, go ahead. You can take this down. It is still with the acceleration scheme. Okay? Just for information. Finish with this? All right. All right, the last two schemes I want to look at, the permissive overreach strip scheme. The key difference here is that the send signal is done using the instantaneous zone 2 contact. That's it. That's the main difference. So the signal send that we had for the permissive underreach, it was done by the zone 1 instantaneous contact. The zone 2, yes, is what is used for the permissive overreach. So the two conditions here are that one, there's a zone 2 occurrence, and the signal is received. So you would have had the operation you'd have had the operation in zone 1 at the zone 1 end, but in terms of of the other end, it would have seen zone 2 and it would have received the signal from the instantaneous zone 2. So the instantaneous zone 2, that is what is sending the signal. All right. So that's the main difference between the overreach. So in terms of the supervision, you can see it in this line here. So you have the instantaneous zone 2 contact, and you have the receive relay contact. Right? And that's the AND function that we have there. I trust you would have recognized that the only point in the solid state logic that changes would be whether you're doing supervision. So at the top, your zone 1, zone 2, and zone 3, those remain the same, and they're all going through an OR gate. Yep. The main difference is what is being used to send the signal and how you are monitoring the signal or supervising the signal. Okay? I'm just giving you some hints as to how to remember these things. All right, you can just get these points. Okay, and now we come to the final scheme, which is your blocking scheme. And everything that we have spoken about so far, the blocking scheme is the direct opposite. So for all the schemes we have looked at zone on extension, we have looked at acceleration, we have looked at permissive underreach, we have looked at direct transfer, we have looked at permissive overreach. All of them, receipt of a signal, those that have supervisory aspect to them, all of them operates by receiving a signal in order to function. Okay, I see you're still writing, my bad. Well, let us, in going to the blocking scheme, let us just refresh ourselves as to what the primary objective is. Primary objective is that we want speedy operation at the remote end. That's our objective. If we achieve that, we're good. So, this is a question I ask every time I teach this. How long does it take to receive nothing? Yeah, it's a stupid question, but I love it. How long does it take to receive nothing? Is that Duncan? How long does it take to receive nothing? Is that Buchanan? It's $1 million question. You know?
Sir, it can be argued that it takes forever because you never know when you actually receive it.
Yeah, but you receive it. Because it's nothing.
You can't receive nothing, so you can.
Yeah. How long does it take to receive nothing? And that is the beauty of the blocking scheme. Because for the transfer trip schemes, yes, the transmitted signals, those signals that we are sending, are always sent to initiate tripping. The blocking scheme, however, the signals are sent to prevent tripping. And so by virtue of my $1 million question, right, it means that the blocking scheme would be the fastest because nothing is received instantaneously. Yeah. So if as we have it here, if you end up with an issue with the communication network, you are unable to send the signal. So it means that you're going to end up with a problem that we indicated earlier. You're gonna have the fault remaining on the system longer than you would have liked on one end. Yes? But you don't want that. So the question is, you know, would the blocking scheme help that? Help to militate against that problem? All right? So the blocking scheme uses what we refer to as inverse logic. We get signals if and only if we need to, or the fault rather, is external. So it's gonna send a signal if the fault is external. And if the fault is external, it means that we are going to be sending this signal, the block signal, on a line that is fully in service. And this is true, or this is helpful if we are using power line carriers. And the power line carriers, all they are doing is superimposing the signal on the power line itself. So if you are able to do that, then, you know, hey, the battle is won. All right, so let us see how this system operates. And the other thing we want to note is that we are using the zone 2. Yeah. So we're using the overreaching zone 2 measuring units. And we want these now to operate instantaneously. So if we receive a signal, it means don't operate. If we don't receive, it means please go ahead, operate. So let's go through the logic circuit. All right, first things first. In this circuit, what you're seeing are some modifications to the ones we looked at earlier. And the biggest modification are shown here. The zone 3 setting are shown in the reverse. So from end H, you have the zone 1H, you have the zone 2H, they're all looking in that direction towards end G. However, at end H, we're looking towards J. At the top, G is zone 3 is looking in the opposite direction, and 1 and 2 are looking in that direction. All right? So the big difference in terms of the settings is that the zone 3 settings are looking in the opposite direction. So let's now look at the logic circuit and the solid state and the contact logic to see how this system works. All right. Okay, now, let me just highlight this line. That line has the zone 2 and the receive relay. Yes? Of course, that contact, that receive relay contact will open if we get a signal. Agree? So it would render the zone 2 inoperable. So if we get a signal, that normally closed contact will open. If we get no signal, then it remains. Are we clear? All right, good. So what I'm going to do is to just go through. There are 3 faults that are shown. And we just want to talk about how the 3 faults would be cleared using the blocking scheme. All right? So let's look at fault R. Where is fault R? Is it in zone 1? And we're looking at G and H. Where is it located?
It's in zone 1, sir, for both.
Absolutely. So how would that fault be cleared?
So the instantaneous zone 1
So it will-
contact is
So it will be instantaneous for both ends. All right, good. Next, let's look now at fault S. Where is fault S located?
Sir, it will be in zone 1 for H and zone 2 for G.
Okay, so in terms of normal operation, what would we have expected?
The instantaneous relay for zone H.
All right, so H would be instantaneous, and it is in, as he said, zone 2 for G. However, look at the solid state logic circuit. Which instantaneous contact are we using to send the signal?
Zone 3, sir.
Zone 3, excellent. So we have zone 3 sending the signal. Now, because of where S is located, yes, would you have received a signal from end H?
No, sir.
Because the reverse looking would be looking down to H to J. Yes? So you'd have a zone 2, which we would have that closed. You'd receive no signal. So it means that this normally closed signal, this normally closed contact would remain closed. And so you'd have instantaneous operation of our trip coil. What do you think?
yes, sir.
Question, Ms. Gray?
No, sir.
Oh, okay. All right, now, let's look at T. Again, where is T located?
Sir,
Zone
zone
1
2 for G and zone 3 for H.
Okay. So it is in zone 3 for H and it's in zone 2 at G. So would I have the instantaneous contact for zone 2 closing?
which relay? So you're talking about H, right?
No, man. Remember, the fault is at T. And we're looking at G. Remember G? Remember, you know, what's the objective? The objective is to clear the fault on the line. Yes? So for fault S, we wanted to see how fast we could open the breaker at G. So with the fault at S, H would have been instantaneous. But G, the zone 2 contact would have closed because the fault at S is in zone 2, as Buchanan said. But you would have received no signal. And so the normally closed contact there, the receive relay contact, would have remained closed. Because remember, the contacts are shown in their unenergized state. So that's for S. But at H, sorry, at T, for T, come on. It's over here. So because it is in zone 2 from G, then this would close. Yes? However, it is also in zone 3 at H. So H would send a signal and this would open. So the receive relay, look at the receive relay. Here's the receive relay. Yeah? So it would have received, so you'd have 1. So the input to the AND gate would be 0. So the output here would be 0. Everybody with me? If you have nothing, if you had 0, find another color. If you had 0, meaning no signal is sent, then the input to the AND gate at this point would be 1. The 1 plus the zone 2 would give you 1. But if you have a signal being sent, as we are showing here, with fault T, it's in zone 3, so the zone 3 would have sent a signal, which is 1, corresponds to a 0, because you have the NOT gate, so it will correspond to a 0 into the AND, which therefore gives you a 0 at the output. Because remember, the blocking scheme only sends a signal if you should not operate. All right? So what we have here is that because the fault is outside of the protected line, then this line would remain in operation. And it would allow the protection on the adjacent line to operate. You see, everything has to tie up, you know. So what we spoke of when we mentioned the whole business of discrimination, remember all of that? We gave all those definitions. We have to maintain that in the protection system that we're looking at. So we want to ensure that only that which you need to take out is removed. The fault is genuinely on HJ, therefore you don't want GH to operate. Good? Now, I've said some things, and it's all right, I understand that you wouldn't challenge me at this stage because you're still learning it. But think about it. Because nothing is instantaneous, isn't it possible that we can have maloperations? Since, as Mr. Buchanan tried to argue, we don't know when nothing is coming, since we're getting nothing. Yeah? That's a nothing argument, I understand. But the point is, we don't know when nothing is coming. So if nothing arrives, we don't know if it has arrived. I hope you are perfectly confused at this point. All right? So, to avoid that, there are some measures that are put in place. Because since I am depending on the communication system to tell me when it is that I should not operate, the first thing I need to ensure is that I know whether or not the communication signal is working. So I have to be sure that it is working. I also have to be sure that I am to receive nothing. And so, whilst I get the zone 2 signal, I just wait a little bit to ensure that nothing is supposed to come. So just in case the nothing took a little longer to arrive, I have a short time delay. So all of those are built into the into the reverse, into the blocking scheme to prevent incorrect operation. We have a short time delay, which we refer to as a short time lag. Yes. We have a channel in service contact, which tells us whether or not the communication system is working properly. Yeah. And all of those are put in series so that we have to check each of these boxes before we operate. So all right, so the short time delay that I mentioned is to ensure that we are indeed not expecting a signal. All right? Because as we started out with my billion-dollar question, nothing is instant. And don't worry, I know I'm ingratiating myself, but hey, a man can put value on his questions. So finally tonight, we just look at what we refer to as a practical blocking scheme. All right? So practical blocking scheme, as I said, we just put all of what I mentioned in series to ensure that we check each box before operation occurs. All right? Because the blocking scheme, in terms of speed, is the fastest of all that we have looked at. In terms, fastest and most secure. The direct transfer would be fastest because it's, well, not really, that's not true because it is sending a signal. But for your blocking, we introduced the short time lag, all right? So this contact, the short time lag, remains open for a time t. So we just delay it slightly. Obviously, this time would be less than your zone 2 timer, all right? Because we are just delaying it slightly to ensure proper operation. You receive relay, which we have already spoken about, and the channel in service, yes? Once the channel is in service, then you know that well, not really, no, but then this path becomes available to us. This operational path becomes available only if the channel in service is working, yeah? Only if we receive nothing, and also after a short delay. And that short delay comes from the zone 2 instantaneous. All right? And this is important. And you know, I have said it quite a few times this evening, and I hope it is now solidified in your minds that our objective is to speed up the operation at the far end. And with that being the case, we have to use the fact that the fault is in that end zone. So we use the zone 2 for our short time lag. Yes, we have the signal received. Yep. Of course, again, you get nothing, then you have 0, which means that you have a 1 there. So you have all 3 giving you a 1 for you to have operation based on the blocking scheme. So students, I know it has been a mouthful this evening. Yes. What I'm going to do, all things being equal, when we meet tomorrow, what I will do is to discuss the communication, the methods of communication, and how we go about selecting what's most appropriate. And yeah, I think we'll be on our way.